In Chapter 3, I'm going to discuss why objects move the way they move and how we can change the way objects move. So I'm going to discuss forces and how they affect the motion of objects. In nature, interactions happen through forces. Forces are everywhere around us. They are a fundamental concept in physics and in technology in general. Without the existence of force, there would be no way for objects to interact with each other. In general, forces can be classified as a pull or a push. So we have pulling forces that can be acting from a distance or through a full contact. And then we also have push forces. Push forces such as, for example, this person here pushing on this cupboard, or somebody pushing a shopping cart, and so on and so forth. It is important to remember and keep in mind that force is a fundamental concept in physics, and we are going to deal with this quantity in different aspects through the course a lot. So the rules, the basic rules and the laws that I'm going to discuss in this chapter apply for any force that we are going to encounter, no matter what type of force it is. It doesn't matter that it's a push force, a pull force, that it acts from a distance or through contact. Now let's give example of some particular forces. Let's first talk about forces that act through contact. So we have friction, which is one of the most common forces in existence. Friction is a force that appears any time there is a contact between the surfaces of two objects and relative motion with respect to one another. Friction is a force that plays a huge role in everyday life because without friction, it would be impossible to walk, move the objects, pick up things, and so on and so forth. And friction also is a force that in certain situations is actually not desirable. For example, in the operation of machines and engines, friction is not desirable because it wears the parts out. Another force that acts through contact is elastic force. Then we have normal force and tension force, or just tension. Now let's list a few examples of forces that act from a distance. So we have gravitational force, electric force, magnetic force, and then there are other forces that are associated with the structure of matter, specifically elementary particles, but we are not going to discuss those forces. So those are the main types of forces that we will discuss during the semester. The units that are used for force are called newtons, and the abbreviation is capital N. The units are named after the English physicist Sir Isaac Newton, who formulated 3 laws of motion, how forces affect the motion of objects, in the 17th century. As we know from the previous lectures, newtons are not a basic unit of measurement in the metric system. Newtons are a derived unit. So later on in the chapter presentation, I will explain what combination of the basic units in the metric system make up the units of newtons. Since forces are defined as either a push or a pull, that indicates that they have direction. And of course they also have magnitude, and so therefore forces are vector quantities. This is a very important property because due to that vector nature, force addition to determine the resultant or net force that acts on a certain object or a system of objects must be done in a specific manner so that the result of that addition is accurate. And so one more time, forces are vector quantities. They have magnitude, and the magnitude is how strong the force is, and direction. And direction is, how the force acts. Does it pull? Does it push? And so you have a good intuition about those properties of force because you have at least once in your life had to move an object. And so you know very well that in order to move an object, you would have to push or pull on that object. And then, depending on how hard you push or pull, the object will move with, more or less, with higher or lower speed, so to say. And a simple example of such action would be pushing a shopping cart. So you know that when your shopping cart is empty, it is very easy to push or pull the shopping cart. It doesn't require much effort to do so, and you know that the direction of motion will be determined on whether you push or pull and how you do that. When your shopping cart is full, however, then you will find out that it takes more effort to push or pull that shopping cart. So larger force is required to perform the same or make the cart moved in the same way as when it was empty. And we're going to come back to this example later when we talk about inertia and mass. Now let's talk about the rules that can be used or that must be used to add two vector quantities to calculate the resultant or net vector quantity. And I'm going to limit the discussion to forces in this example. However, this rule also applies for displacement and other vector quantities as well. So the vector addition rule, I'm going to call tail to head rule. So let's explain what that is. Actually, let's define it first, and then we'll explain it. So the tail to head rule states that to add two vectors, place the tail of the second vector at the head of the first vector. The resultant, or net vector, will have its tail at the tail of the first vector and its head at the head of the second vector. So one more time. To add two vectors, place the tail of the second vector at the head of the first vector. The resultant or net vector will have its tail at the tail of the first vector and its head at the head of the second vector. So when we talk about the first and the second vector, what does that mean? Before I answer this question, let's talk about how we represent vectors. A vector quantity, graphically, is represented by an arrow with length equal to the magnitude of the vector itself and direction determined by the direction of the arrowhead of this arrow. So again, a vector quantity is graphically represented by an arrow. The length of the arrow is equal to the magnitude of the vector quantity and the direction is given by the arrow. So let's do one of those vector quantities. So here is the arrow, and let's call the vector quantity A. And the label also, in order to indicate that it's a vector quantity, requires that we put a small arrow on top. And so the length of this line here would represent the magnitude of that vector quantity, and the direction is given by the arrowhead. So the length is equal to the magnitude and this gives us the direction of the vector quantity. And again, the label is a letter of choice depending on what the physical quantity you're dealing with is. And then on top, we put a small arrow to indicate it's a vector quantity. So now let's apply the tail to head rule to add two vector quantities graphically. So let's consider that. Let's consider two vector quantities. Let's call the first one A and the second one B. And so these vector quantities can be forces, they can be displacements, they can be velocities, they can be anything. The important part is that they are vector quantities. So I want to find the sum of those two. And so I will write this as A plus B. And let's call the resultant vector C. So the tail to head rule stated that I take the second vector and place its tail at the head of the first vector, and then the resultant vector has its tail at the tail of the first vector and its head at the head of the second vector. So what is the first vector and what is the second vector? Well, this is determined by the order in which the two are written in the sum. So in this particular example, A is the first vector and B is the second vector. So then, how can I execute the rule that defines how the two vectors are added? Very simply, I'm just going to take vector B and slide it parallel to itself until its tail is at the head of A. So that will look something like so. So this is A, this is B, and now I have the tail of B at the head of A. So I just simply, one more time, I just simply took B and slid it parallel to itself until its tail touched the head of A. One thing that I cannot do, I'm not allowed to do by the rule, is rotate B. So if I'm going to move it in space, it has to be parallel to itself. When that is done, the vector doesn't change. So once I have the two vectors like so, then by definition the resultant vector C starts at the tail of A and ends at the head of B. And so C, which is equal to A plus B, looks like so. Similarly, I can add more than two vectors. For example, I have vector A, vector B, and vector D. And I want to find the resultant vector, which is A plus B plus D, and let's call this one R. So the rule applies just the same. I'm going to take vector B and slide it parallel to itself until its tail touches the head of A. Then I'm going to take vector D and I'm going to slide it parallel to itself until its tail touches the head of B. And then the resultant vector R will start at the tail of A and end at the head of D. So let's sketch that. So we have A, then I take B and I slide it until its tail touches the head of A. And then I take D and slide it parallel to itself until its tail touches the head of B. And then the resultant vector R starts from at A and ends at D. This method of adding vectors is not very accurate because it does not give us exact length of the resultant vector. It doesn't give us the orientation of the resultant vector in space exactly. However, this method is good to give us a general understanding of where the resultant vector is in space when vectors are added together. It is beyond the scope of this course to determine exactly the magnitude of the resultant vector and the direction in space. So therefore, we are going to limit ourselves with discussions of that sort only. The discussion of the rule of addition vectors that I showed here with those two examples can be applied for actual physical quantities. However, since when we are dealing with vectors in physics, we need to have a reference frame or a map with respect to which we are positioning these vector quantities, and we are measuring parameters. We have to introduce such map in order to add, let's say, displacement vectors. And so let's do one example that shows how this is applied for addition of the displacement vector of a runner. So here's the example. A runner ran 2,000 meters due north, then she stopped for a water break and then ran for another 1,000 meters due north after that. What was the net displacement of the runner? So in order to be able to add the two vectors, the two displacement together, let's introduce a map. And the map is very simple. It's simply a geographical map with east, west, north, and south directions. And so the runner ran north initially for 2,000 meters. So let's extend the north direction a little bit. So 2,000 meters due north, then she stopped for a little bit, then ran another 1,000 meters. And so the question is, what's the displacement? So here I can use straight up the definition of vector addition, because here I'm adding two vectors. So the definition was the tail to head definition. You take the second vector, you place its tail at the head of the first vector, and then the resultant vector starts at the tail of the first vector and ends at the head of the second vector. So by that definition, that would be this vector, and this vector will have magnitude of 2,000 plus 1,000, so that is 3,000 meters. Now I can do a different example in which the runner is moving differently. So let's do that. So let the runner from the previous example run back 1,000 meters after the water break. So find the net displacement. Let's draw our map again, our coordinate system. So we have north and south, and then we have east and west, east and west. So initially the runner ran 2,000 meters due north, but then she ran 1,000 meters due south. So she went in south direction. So then what is the net displacement? Well, from the rule of addition of vectors, we place the tail of the second vector, that's the 1,000 meters, at the head of the first vector, that's the 2,000 meters, and then the resultant vector starts at the head, at the tail of the first vector and at the head of the second vector. So that is the resultant vector right here. And so the resultant vector is with magnitude of 2,000 meters this way minus 1,000 meters the other way. So the magnitude is 1,000 meters. So as you can see, the direction of the vectors matters for addition of vectors. If we were talking only about the distance that the runner covered, that is just the length of path from the starting or the initial position to the final position, that would be simply 2,000 meters plus 1,000, 3,000 meters. And it doesn't matter how the runner ran. In the previous example, the total distance traveled would be 3,000 meters. In this example, also 3,000 meters. But the displacements are different, and that is because they are vector quantities. The same reasoning can be applied for forces as well, or for other vector quantities. So when we are dealing with those types of additions, vector quantities, we always must introduce a coordinate system. In the specific example here with the runner, the coordinate system is simply a geographical map with directions east, north, west, and south. But in general, when we are dealing with vector quantities, all that is necessary is to introduce a coordinate system like so, and in that coordinate system we only need to indicate positive direction and negative direction. Once that is done, all forces that point in positive direction, when doing calculations with them, are taken with a positive sign, and all forces or other vectors that point in negative direction will be taken with negative signs. And then when the addition of the values or the magnitudes happen, the signs are accounted for accordingly, and then the result will be just due to performing simple algebraic addition, and that's how we get the net force. So we will see. We'll do a quick example showing this type of calculation with forces just to illustrate the concept.